Hi, this is Abousamra, and I'm presenting our paper, Localization in the Crowd with Topological Constraints. Crowd localization is about finding the location of each person in a crowded scene, where the ground truth is in the form of a single dot on each head like we see on the right. The solution of localization naturally solves the crowd counting problem, where the target is the total number of people in the image. Crowd localization can be further extended beyond people to any dense population such as animals or biological cells, and is important for conducting any spatial analysis on the population. There are several challenges in crowd localization. Perspective, occlusion, and cluttering are some of the fundamental challenges in a crowded scene. If we look at the zoomed-in image, we see that the ground truth dots can be randomly perturbed as long as they are on the target instances. It can be on the hair, on the cheek, or even on hands, and so the features of the dots are not specific. With this kind of supervision, it is difficult to prevent spatial semantic errors. In this example, when you try to directly predict the dots, we get two predictions for the same person. One of them is a false positive. In the second example, the predictions for the two left dots collapse to appear as one in the prediction mask. And so we get a false negative. In this work, we try to address these challenges. Our contributions are as follows. We formulate crowd localization as a structured prediction problem. We introduce topological constraints in order to solve explicitly the possible semantic errors. We show that our proposed model, TopoCount, achieves state-of-the-art localization accuracy. We show that it complements well counting specific methods and can be easily integrated to improve their counting performance. Our proposed method, TopoCount, tries to directly predict the dots. As we see, the ground truth has a dot for each person in the image. And so we train a neural network model with ground truth maps where we slightly dilate the dots to get larger components with the condition that the resulting components do not overlap to ensure topological correctness, like this. Each dilated dot is considered as a connected component, and the output of the model is a binary mask, where also each connected component in the mask represents one dot. We formulate the topological constraint for crowd localization as follows. Within any local patch, the number of connected components in the prediction should equal to the number of ground truth dots. This constraint efficiently encodes the spatial configuration of the dots without being too specific about their locations. If we look at the example on the left, the ground truth has 3 dots, and the prediction mask before training with the topological constraint has 4 components. One of them is a false positive. After training with the topological constraint, the false prediction disappears, and we are left with the correct number of components. On the right, the ground truth has 4 components, and the prediction mask before the topological constraint has 3 connected components, because 2 of the predictions collapse to appear as one in the prediction mask. After training with the topological constraint, the components become well separated and have the same number as the ground truth. These are topological errors, and they correspond to semantic errors. And so by training our model to avoid topological errors, we are training the model to avoid the semantic errors. In order to enforce the topological constraint, we propose persistence loss. Instead of looking at the topography or prediction mask, we look at the topography or the bumpiness of the likelihood function, where each bump in the 3D likelihood function corresponds to a mode, and the values correspond to saddle points. Each mode in the likelihood function corresponds to a possible dot prediction. To get the prediction mask, we apply a threshold. Everything above the threshold plane will become 1 in the prediction mask, and everything below the threshold will become 0. In this example, the two modes M1, M2, and the saddle point between them are all above the threshold plane, and so the predictions corresponding to the two modes collapse in the prediction mask to appear as 1. The fifth mode, M5, is below the threshold, and so it disappears from the prediction mask. What we want here is to have 4 modes corresponding to the 4 dots in the ground truth. And this is exactly what the persistence loss will do. The persistence loss captures all the modes in the likelihood function and chooses to suppress or enhance them in order to bring the number of components in the prediction to be the same as the ground truth. And in this example, the ground truth has 4 dots. And so the persistence loss will enhance the top 4 salient modes with the highest bound and will suppress the fifth mode, M5. And after training with the persistence loss, as we'll show later, the result will be that the 4 top salient modes will have higher saliency, and the prediction mask will have better separated components. We mentioned the saliency of the modes. What is the saliency of a mode? According to persistence homology theory, the saliency or persistence of a mode is measured by its relative height. It's the difference between the function value of the mode and a nearby saddle point. The pairs of modes and saddle points can be computed according to the persistence homology filtration algorithm. And so in a local patch, if we have C ground truth dots, the persistence loss will reinforce the total saliency of the top C modes and suppress the saliency of the rest. Formally, given a patch with C ground truth dots, the persistence loss equals the negative sum of the persistence of the top C modes plus the sum of the persistence of the remaining modes. And so we train our model with the persistence loss to learn to fix the errors in the prediction. But to get such a prediction, we also need an additional pixel-wise loss. We use a dice loss, which is more robust to segmentation imbalance. And the overall loss becomes the weighted sum of the dice loss and the persistence loss. Our model is a convolutional neural network with a UNet-style architecture and a VGG16 encoder. The likelihood map is obtained by applying an sigmoid activation on the output of the convolutional neural network. Next, we discuss the experiments and evaluation. We evaluate our model, our proposed method, on several benchmarks, including Shanghai Tech, UCF CC50, UCF QNRF, GHU++, and the NWPU challenge. We evaluate our proposed method on both the localization task and the counting task. We first evaluate the localized counting. We use the grid average mean absolute error, GOM. It divides the image into grid cells and captures the correctness of the count on the cell level. The grid size increases with increase in level L, so that G of 0 is the whole image and G of 3 is an 8 by 8 grid. We compare against crowd counting and crowd localization methods. And we show that we achieve the lowest error, especially at the smallest cell level, a cell size G of 3. We also use the same metric to conduct an ablation study on the loss function. We compare the pixel-wise loss using binary cross entropy loss, and pixel-wise loss using dice loss, and the dice loss plus the persistence loss. We see that the dice loss with the persistence loss achieves the lowest error. We also evaluate the dot matching accuracy using the precision, recall, and F-score. It should be noted that a prediction need not be exactly coinciding with the ground truth dot in order to be considered correct. A prediction is correct as long as it is on the target person. And so there are different measures in the literature for matching the ground truth for matching the prediction dots to the ground truth dots. We show here the results from the NWPU crowd localization challenge. The NWPU dataset has both dot annotation and bounding box annotation. They propose an adaptive matching threshold, sigma L or sigma large, or sigma S or sigma small, as functions of the bounding box dimensions, where sigma S is more strict. A prediction is considered positive, a true positive prediction, if it is within matching distance from the ground truth. We evaluate on both the sigma L and sigma S measures and achieve the highest F-score in both metrics. Next, we evaluate the counting performance. We evaluate using two solutions. First, the trivial counting solution, where we just count the number of predicted dots. And second, the integration with density map-based counting methods. State-of-the-art counting methods predict a density map that is a mixture of Gaussians, where the estimated count is the sum of the density map. These methods are optimized to perform well on the counting task without being concerned about the exact location of people in the image. We propose a simple integration where we provide the results from TopoCount as additional input to the counting models. We first show the performance of the trivial solution of counting the number of predicted dots. We find that we beat the state-of-the-art on the GHU++ dataset and achieve close performance to the state-of-the-art methods on the other datasets. For the integration solution, we integrate with two of last year's state-of-the-art density map-based methods, namely context-aware crowd counting and Bayesian loss for crowd count estimation. We show here the mean absolute error and root mean squared error for the baselines of only the counting methods without the integration. After the integration with TopoCount, the errors are reduced significantly, with up to 28% improvement in the error. Furthermore, we achieve state-of-the-art performance on 3 datasets. Here we show a qualitative result showing how the integration can benefit the counting performance. In this example, the baseline density map performs poorly because of the strong shadow in the circled region. After the integration, the counting error is reduced by almost 80%. Here we show some qualitative results from TopoCount. We have the input image and the ground truth dots and the count. And on the right, we have the prediction mask We show that with different and heterogeneous densities, we achieve very good performance with TopoCount. We also show that with difficult images that have very dense regions and snowy weather, TopoCount also works well in these conditions. To conclude, we introduce topological constraints in order to explicitly solve possible topological and semantic errors in the prediction. In order to enforce the topological constraint, we propose a novel persistence loss based on the persistence homology theory. We show that our proposed method achieves state-of-the-art localization accuracy, and we show that our proposed method provides valuable information for crowd counting methods and can be easily integrated to improve their counting performance. For future work, we want to try our method on other applications such as tumor microenvironment analysis and social distancing monitoring. Thank you for listening to our talk. Please find here the link to our code and contact email.